Okay. Ah, you can all hear it properly. Sound is okay? Yeah. Okay. These are two questions one typically will ask when you wake up early in the morning suddenly. They say, where am I and what time is it? Why? And it's almost philosophical. But that's not what I'm going to talk about. I'm going to talk about welcome to global positioning system. Okay, this is something which will use, all of you must have heard about what GPS is and so on. What I'm going to do is to describe what are the physical principles which are used in order to make such a system viable. So the system works, everybody knows it, you turn on your mobile and use it, but how does it work? Not just mechanism of working, but what does it depend on? And that's what I'm going to describe. So the focus will be on global positioning system. Now let's start first. This is very sophisticated system and so on. So one natural question is, well, why do you need to do that? And that's because in modern societies, where you have a large number of people spread all over the globe, doing all kinds of things, they need to have precise timing. You need to know what time is it. That is the second part of the question. And you need to also have synchronization. It's not enough to say that your watch is fine and your watch is fine, but we should make sure that our watches are coordinated. Not only they agree when you start, but they maintain the relation between those very stably. These two things are absolutely essential. So where are these things needed? Well, these are essential in navigation. As all of you will know, use GPS for various things, but that is only going in the city travel and so on. You need much more for traveling by flights or keeping track of which trains are going where, how to coordinate them, schedule them and so on. So traveling is that requires navigation. That's one place this is precise timing and sequential. Tracking mobile resources, you are having all kinds of shipping, oil, lots of grains, whatever you have, minerals, etc. They are all going to be transported from one end of the world to the second and all over the place. You need to track, or even within the city. Something is being transported, some grocery is going from point A to point B. You say, where is the truck? Why is it not coming? You can track it. So you need to tracking mobile resources, that is transport sector, banking and financial markets. This will be hard to imagine why GPS-like thing is necessary for this. But it is because many of the financial transactions that you do, for example, I write a check to you and you go and deposit. Nobody writes checks these days, but let's say momentarily. Or I transfer some money to you and say, I have transferred the money, now you can pay something to somebody. But you say, when I try to do that, I have not received it. So then you say, okay, you have written something which is not valid, illegal, so there is a problem. So you need to have precise timing as to when the money is sent, deposited, and when it's transferred. If you don't have that thing, then there is a problem of ascertaining who made a mistake, who should be penalized, and so on and so forth. So these things are essential for that. So sequence of transactions have to be very precisely timed. Power distribution grids. You have power going all over the place. There are power sources, generators of hydroelectric, wind energy, whatever it is, all over the place. Big grids, national level grids, or even regional grids. And if they are not properly synchronized, if they don't maintain the frequency of their power, AC current is what is used for transporting, then the grid failures occur. Now you want to know where is it going off, which place it has happened, and am I having the two grids which are connected, let's say southern grid and western grid, are they connected properly, are they synchronized? If they are not, then this happens. Actually in the late 90s, this was a problem. Typically, the then Andhra Pradesh would draw, some problem will be there in their distribution system, and suddenly the southern entire grid will trip and will lose power. So that time they say, oh, the frequency was supposed to be maintained between whatever 48 hertz or something, 48 to 52 or something, and it went below that. I never understood that time what it meant. Now I do. But that is where, in order to detect and keep it proper, you need this precise timing. And of course, large-scale agriculture. This will be very hard to imagine. Why would you need something like GPS thing for agriculture? Well, if you have really large farms, then you need to worry about how we are going to do watering the plants and the fields, how are you going to put the fertilizers, how are you going to pesticides, you have to manage it, where are you going to start cutting, keeping track of all of this when the scale is very large. Yesterday, for fun, I just checked what is the largest farm in India, and I don't know how reliable it is. It's after all Google information. It says there is a place in Rajasthan, and the size is about 10,000 acres. So 1 acre is about half a hectare. 1 hectare is 100 meter by 100 meter. Now you convert to see what dimensions it should be roughly. Okay. So I said, okay, fine, this it didn't look very large, 10,000, large number. I said, okay, what about in the world? And can you make a guess? Well, the largest one, again, as per the Google, to the extent it is true, is in China, and that is 22 million acres. 22 million acres. Okay, that's the largest. And there are many in Australia, etc., which are all, the large ones are all in the class of million. We are talking about 10,000, 100 times more than that. So if you anything of that, obviously it's not owned by one person or something, and it's not managed by one person. That's out of question. There will be various things. Those things I didn't look at. But if you are managing resources of that kind, then you need to have synchronization of activities, and that requires precise timing. So that is the reason for modern societies, which meaning large scale things are there, you need to do all that. So this needs accurately and stably ticking clocks and synchronization of widely separated clocks. Clocks are all over the place. I am using my clock, other clock is 1,000 kilometers away, they should be synchronized. How do you do that? So first need is addressed by atomic clocks, while the second is addressed by global positioning system. There are multiple systems, so I just put it in double quotes to say that there are so many different systems. So global positioning system is what is needed in order to do synchronization and to make the precision of the clock in the atomic clocks. So these two things are needed in order to address all this. Okay, so having sort of given the motivation and setting the stage as to why these things are important at all, let's go to the simplest. We'll now go to the sort of classroom and say, okay, let's start talking about some toy problems and see how to handle it. So let's say the problem of navigation. Imagine you are touring a new place. We have got a map of the place. Many of us nowadays, you just use the mobile and look at the map. But earlier days, we'll take physically map and go to some place. Here is a map and start saying, where am I? Okay. And we know where we want to go, but we get lost. What does it mean we get lost? We get lost meaning we have the map, but we don't know where on the map we are. You might have seen when you go to, either you might have gone to zoos or museums or something. Usually you will go to some place and say, you are here. They will show the map and say, you are here. That here is important. Because without that, you don't know where to go. So you need to find out, that is what it means to say getting lost. Okay. Now, if we could locate ourselves on the map, then we can find out, oh, here is alternative route, I can take the route and go. Then there's no problem, right? So I need to find out, locate myself on the map. Map is with me. How do we find our location on the map? That's the problem of navigation. If I know that, then I have a chance of doing something. So I need to have a map, I need to have a method of locating myself, and then of course I should have means to go wherever I want to go. That's a separate problem. Okay, well, here is let's break down the problem. So I need map, that requires geometry because I need to know distances, how far I have to go and so on and so forth. And I need space time, okay. Now, this happens, relativity has to be incorporated. Why is it incorporated? We'll come to as we go along. I will explain that. This must be, you cannot ignore it. Even if you didn't know, you will have to face it. The space-time of GPS, the actual GPS, what kind of space-time does it use? I will describe that. It's easy to describe, it doesn't need too much of information. I will give whatever is needed. And then I will describe a specific GPS which has been operating, this is called American one, the NASTAR. And then we'll come back to the time transfer. How do you synchronize? So that's the last part I will come to. Okay, so first part is positioning. Okay, here is one thing. I have the map with me. I have some locations, some towers or something. And I have some means of finding out the distance from that particular landmark to wherever I am. I don't know where I am, but I see there is a time, the distance between this is so much, distance between that is so much, and so on. I have means of finding out. Suppose you have those means, and I know whether those landmarks are, their locations are. The locations are supposed to be x1, y1. I'm looking at two-dimensional example. Three-dimensional will be easy to see. And the distance between that location and wherever I am is supposed to be r1. That I'm supposed to know somehow. We'll see how to know that, but later. Then I know another landmark, which is x2, y2. And from that also I know the distance, which is r2. So if I know these two, I know I could be either there. Where is the top one? I could be either there or I could be here. I don't know where I am still. I need one more location. At the third point from where I know the distance, then I know, I must be there because that is the only point from which I get the three distances which are measured and they're consistent with the map positions which are there. So all I need to know is I have to find out this equation, distance between, the lengths between these, and solve this simultaneous equation to know my unknowns are capital X, capital Y. This I don't know, that's where I am, my location on the map. Other things are supposed to be known. So if I can find out what are the distances, then I'm done. At least I know in principle how to do it. Okay. This is for two-dimensional, so if you're just going on surface, this is sufficient. Okay. Now we go to global one. So this is only just a mechanism by which you can, this is a procedure, not the only procedure, by which you can do it. So let's recall, positioning always means determining coordinates on a predetermined map. So map should be somehow constructed. Then I should have the coordinates and I should know how to determine myself where I am. There must be adequately easily identifiable landmarks like those two x1, y1, x2, y2 I said. They should be known. Their map position should be known. Okay? Otherwise I can't find that thing. Third thing should be we have a method of determining the distance from those landmarks with sufficiently good precision. The best, as precise as we get, then we get the better location, otherwise we don't get it. Global positioning means put the landmarks in space, that is satellites, such that at least 4 are accessible because we are talking about no three-dimensional position. We are not just on plane, but we could be flying in the air or by. So we need at least 4 should be accessible from any region. Okay, that's what we want. And we must now use, because they are far away, I cannot put meter sticks and something, I must use light travel time to determine the distances to the satellite. Okay, so we see how progressively what we need, what are the things essential, what the problem is, and what are the things we need to have in order to make it work. So this is what we need, all right? How do you find the light travel time? Okay, here it is. This is the satellite, which keeps transmitting some signal. Okay, what does it transmit? Transmit some signal like this. Okay, some coded signal with something, some music, whatever it is. Never mind the details. I mean, details are there obviously, but schematically it's transmitting some signal. And it comes down to my mobile term. My mobile device also has a generator which knows what signals are coming, what signals are expected. So it knows the signals will be this. It will identify what I am receiving and say, oh, it must be satellite number 5 or whatever, because the signal itself contains which satellite is coming from. So I know this signal, so I know it is coming. This is the signal that I receive. On my mobile, I will keep generating that signal. There is a difference between these two. They are not aligned. Because this is what it says and this is what is received. So the difference between this must be the travel time. So that's how it took. I don't send message to the satellite, ask hey, where am I? I don't do that. The satellite is doing its job, I do my job. I simply infer it by knowing that I must use the known signal. I generate it myself, find the alignment of this and get the time. Okay? So that's how it is decided. Of course, this will work provided I know when to start generating my signal. Because I could generate it here, start from here, then my answer will be wrong. So I must synchronize where I should generate, my time when I start, and the time with the satellite must be matched. Otherwise, the difference has no meaning. Right? So I need synchronization of that. How you do that? There is a procedure for that, etc. But you understand what is the methodology used. I need to use the light travel time. If I can determine that, I will know the distance. To determine that, this is the simplest method I do, displacement in the signal pattern. And I can do it precisely, provided I know when to start my signal. This is coming at some. It's telling also today's time is so many seconds after 9 o'clock or something. My watch says, oh, it's 9 hours, little bit different. This difference must be that. But my time and that satellite informed tight. They should be synchronized, only then this difference has a meaning. Otherwise, difference has no meaning. If difference has no meaning, I don't know what light travel time is, and then I don't know what is the distance. So I need to know synchronization. Okay, but this is the scheme by which I can determine the light. Okay, that's the need for synchronization. Depends on very much crucial and synchronization of clocks. Not just particular satellite to me, but all the satellites among themselves, because I could be getting signals from all over the place. I need 4 in order to locate myself, right? This means the clock should stick stably, which means if they start tuck, 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 it suddenly went tuck, 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 tuck. It should not do that. It should go exactly that. All of them should maintain their tick frequency exactly same, as stable as possible. And they are not displaced. One is not going twice as fast as other or something. So they should pass the same thing. The rate should be same and the rate should be maintained. There's no drift in the frequency. That's what is essential. The clocks on board of the satellites are highly stable and accurate atomic clocks. While typical receivers have stable clocks like quartz clocks, but they are not as accurate, but then they can reset it. There is a method of resetting it by taking the signal and say, oh, time should be this, I adjust myself. But it is stable. Once I adjust it, it will last at least for, let's say, 24 hours or whatever is the time. Then after that, I reset it again. So it's possible to do so. And this is cheaper, but that other ones are very expensive. We are now more directly dependent on laws of nature. governing the propagation of electromagnetic waves and rates of physical clocks. Without this, rest of the mechanism or scheme that we thought of simply will not work. And we still have to address the issue of maps or coordinate system. I said we need to position ourselves on the map. How do we construct the map? What do you mean by map? So let's have a digression on that. This is something that we keep aside. We need to find out how to handle this. We need to also look at what is meant by map. Okay, so here is a digression. So map means first I have to assign coordinates. I have to say this is longitude, latitude, or whatever it is. Some coordinates I have to assign. And what is the obvious method to do? Again in 2 dimension. Well, choose the origin somewhere, I stand somewhere, to 90 degree angle. I walk there 5 steps, I walk there 5 steps, walk there 5 steps, and so on. So I go either this way, X steps, Y steps here. You come and say, oh, I don't like doing this way. I'll go this way first, and then go this way. Same number of steps, and lo and behold, you come to the same spot. So the procedure of assigning the XY locations to this particular point, it doesn't depend upon whether I go this way first or that way first. I'll get the same answer. So it's okay, it's good because I don't have to worry about whether I should always go right first or left first. I can do either way. Okay? But the simplest procedure fails. Moment it is no longer plane, but it's a sphere. Why? Again, I have the same. This is where I start with. This is one particular case. You can several. I start from here. This is my origin. What was there earlier? I go this way or that way. I go same number of steps. And after going 5 steps, I turn left. Here go up, turn right. But you don't come at the same point. So now it matters. What coordinate am I going to assign to this guy or this guy? If I say XY is so and so, longitude, latitude, is it this point or that point? I don't know. That depends now on the procedure of adopted to assigning the coordinates. Okay? That looks very dangerous because now you have to standardize the procedure somehow and everybody should agree on that. They should all understand what you mean by left and right and all kinds of things issue will come, right? So there is another mathematicians being mathematicians, they say, all right, we don't have to do that. We can adopt a general procedure. What? Take a graph paper, put whatever agreed on that, and stick it on whatever surface you want to do it. In our case, sphere or more general. Whatever number is under that graph paper is the coordinate of the point. Because first thing I want is that I must have a unique assignment of coordinates to a point. Sphere case we saw we have 2 different methods of doing it, 2 different numbers. I don't want that. I must ensure that a given point must have a unique pair of coordinates. So I say the simplest is take a graph paper and stick it on that. At least I ensure that part. Right? Graph paper can be arbitrary, sticking can be arbitrary and so on and so forth. And there is one more problem. Yeah. Yes, you have to take a small enough piece and then stick it. Large piece you cannot. You are absolutely right because it won't fit on that. Correct. So that is what is called, you define the coordinates in a small region and then say, then I must know how to go from these coordinates to those coordinates to that coordinate. I must do that. That requires a coordinate transformation, which is something which is also to be done. We won't need that because right now I'm focusing on a different aspect, but you are absolutely right. I cannot do it on the sphere. I cannot take one graph paper and put it on the sphere and say, here I am. No, I cannot do that. I can do only in small enough places, then I can do it approximately. Absolutely right. Okay. So this is one procedure. Fine, there are many ambiguities how to do that, how we'll put it, what graph paper you use, what scale you use, various things will be there. Those are all handled, give it to mathematician friends and say, you need charts and you can make differentiable transformations, go from one set of coordinate system to other set of coordinate system, then you can transform something, blah, 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 a lot of things happen. That is not the point I want to focus on, because there is some other issue involved in that for our problem. That other issue is, the coordinates can be arbitrary, but now the difference between 2 coordinates, neighboring points, whatever I assign, and the length between the distance between those physical length, the thing is lost because my coordinates are arbitrary. Previously, I walked so many steps, I knew one step is whatever, half a meter or something. So I know the distance I'm traveling. Here I don't know because my grid is arbitrary. Anybody can do whatever grid. So I lost the information about how to measure the distance between the 2 points. I must do some address that issue. Okay? Yeah. You can stretch it, but then yeah, in principle, yes, you can stretchable. I agree. I didn't want to complicate more. Yes, absolutely. Either you can make it small one. What he's saying is that you can don't take the paper to be actual paper, take a rubber sheet. On that you put your grid. So it can stretch a little bit, but who says it has to be uniform? It doesn't have to be uniform. All I want is a unique pair of numbers to be assigned to unique pair of numbers. So if that is the case, I can do that. Thank you. You understand? You understand the answer? Yeah. So either if you take a real paper and try to do it, what you say is completely right, and I can only do it in small pieces. But if a stretchable piece, like a rubber sheet, then I can still do it. Anyway, again, coming back to the point that I'm interested in, the relation between the coordinates, differences, and lengths is non-obvious. Okay? Enter the metric. Now we need to introduce the metric. Example of polar coordinates show. Here is my polar coordinates. Here's a line we choose arbitrarily and start measuring angles from this. Here is the point, coordinates denoted r and theta. You walk in some direction, so many units. Angles we know, use your whatever protractor, whatever it's called. And you get that. R theta, neighboring point is r theta plus delta theta. This is r plus delta r, theta plus neighboring points, coordinates are this. Now these are the points, I want to know what is the distance between them. This I know is delta r, coordinate difference. This is r times delta theta. You know arc length is radius times the angle, right? You learned in geometry. Fine. So the distance between these 2 points, therefore, then Pythagoras will tell you this dr square plus r square delta theta square. So I know the distance between this point and this point, right? This is this one. I can now rewrite that to, yeah. Oops. No. I can rewrite this because I want to generalize. Then you want to make the notation compact as some coefficients called gij, delta xi, delta xj. This is quadratic, so I can need 2 of those deltas. And ij goes from 1 to 2. Each I will go from 1 and 1, 1, 2, 2, 1, 2, 2, 1. So 4 terms will be there, of which I not equal to j is 0 in this case. So delta, g11 will be delta 1 square, which is delta r square. g11 is 1. And g22 is r square, whereas delta theta square is second term. In general, I will write it like this. Okay, this is the simplest example, but I can generalize because my coordinate system is special. If I have a different coordinate system, I need to choose my rules differently, right? Okay, fine. So a map consists of, therefore, so we have assembled some ingredients. I need unique location, unique assignment. I need some method of finding the distances. So coordinates, metric, and a map. A map consists of set of locations being assigned a unique set of numbers together with a metric, which will give a rule to relate coordinate differences to the actual distances, this measurement. Okay. A different set of coordinate assignments, like somebody has a different grid, we need a different metric coefficients in order to give the same distance between the 2 points. I don't want that distance to change. My description of the thing can change, but not the distance. Right? So if I'm going from there to there, it should be exactly, if I'm driving a car, it should be exactly so many kilometers should be there, whether I go this way or that way. So my calculation method is given by the previous one, but it says that I must choose a different metric, appropriately chosen so that this result is true. How to do that is a mathematical technique. Conclusion, coordinates have meaning only in conjunction with the metric coefficient. Coordinate by themselves have no meaning. So my initial problem, I took arbitrary grid and stuck it. That doesn't matter. You can do it because by themselves they have no meaning. Their purpose is only to assign unique numbers. Real meaning will come once I introduce a metric and say, now I can use it and say this is the distance. So I need both in order to say that. Now the question is, okay, maps cannot be mandated arbitrarily, but must conform to the physical properties of region of interest. Like previously, the plane case was there, did not work for the sphere. Tomorrow you may have more complicated things. Okay? So I cannot arbitrarily choose something, but I must choose something which is compatible with what is physically there. How you do that? A set of problems. Okay? So you see what are the steps which are needed in order to get to the positioning system. We are not there yet. We have a long way to go. Okay? So here is an example. Okay, so our map, light and relativity, where does it enter, is what I'm describing now. Recall that satellites are far away in space and distance determines light, which has 2 crucial properties. Light is electromagnetic waves. It is governed by Maxwell's equations and propagates even in vacuum. These facts we have to accept as some facts of nature. Its speed is in vacuum is first of all finite and is independent of speed of the source. So if I move this thing, the speed doesn't change. If I am receiving, speed doesn't change. That is constant. Not only the assignments of spatial coordinates, which require my x, y, z coordinates or locations to be given, I am putting also timestamps because I want to find out when the signal is starting. It's not enough to know where it is, when is it starting and when is it. So I need 4 numbers. So I need to have timestamps. But that depends, both of these things depend on the observer. First, because what grid you choose and how you choose the metric is one observer. But now it says that, because I can't just say one time and the same time will be there because speed of light being constant tells me that you can't do that. It depends upon who is moving. All right. Thanks to the universality of speed of light, now our maps must be regarded not as, first it was 2-dimensional, not 3-dimensional, but 4-dimensional, which means I must assign 4 numbers to talk about events of interest, and then I must give a metric to talk about distances between them. What kind of distances? They can be either distances in kilometers or meters, or they can be how many seconds difference is there. So 2 types of things, time intervals as well as length intervals. Okay. So thing has to be 4-dimensional. All right. Here is the example now. Okay. This is special relativity. So map according to special relativity. What is the map? Give me coordinates and give me the metric. If you give me that, I'll set up my map at least. So let's assume somehow I managed to do that, because I'm trying to see how the special relativity impacts in physical interpretations. Okay. So let's say somehow we have managed to get this t(x,y,z), and this particular quantity is the one which is telling us what is the distance between coordinate differences. If 2 events have differences, their time coordinates change by delta t, the space coordinates change delta x, delta y, delta z, then this particular combination is I'm going to call the distance. Okay. Now, unlike the earlier distances we talked about, which are always positive, here it is not. It can be positive, negative, or 0, because I have time which is not same as space. Why did I choose this particular one? Because this is the one which Einstein comes and say, oh, speed of light is constant. So this quantity is invariant. Remember I said that my metric assignment must be such that if I change the coordinates and change the metric, they should give the same interval. If I have 2 different coordinate systems, I put one grid, you put another grid, then you say, aha, but I will choose this metric, you will choose this metric. Together they must be such that we talk about same distance between 2 given points. That has to be ensured, which means they must transform in a particular fashion. They cannot arbitrarily transform. If so, there should be some quantity which is invariant. What is the invariant? This is the invariant. That is special relativity, which says the speed of light being constant, this quantity is invariant. Okay. This is something, the details of this you will study, or maybe I think he is going to give a talk on Sunday. He will explain this in more detail as to why this is invariant and so on and so forth. Let's for the moment assume this is there. Somehow I talked to him earlier and he said, okay, put this metric, so I put this metric. I'm going to use this and say, suppose somebody comes and gives me, how do I use it? What does it mean? Well, this is what it means. It implies that moving clocks will tick at a slower rate. Just this expression alone tells you that. Well, how is that, right? And why is that the case? Well, let's do one thing. Take C delta outside and becomes 1 minus and divide delta x by delta t, delta y by delta t, and delta z by delta t as speed. So that's a coordinate speed, right? I have distances, I have markings on the road, I go by car and find out how much time I take, that's my speed. So my speed is this, v dot v, that is v1 square plus v2 square plus v3 square. I have taken out the factor of c, so it's c square, and this is taken out, so it is 1 minus all of that, and take square root. That gives me this expression. It's just simple algebra, right? But now, I told you that coordinates have meaning only in conjunction with a metric. I have not told you how the coordinates are assigned or what they mean. I only said some coordinates are there, some metric is there, this is what the answer is, and this is given to be invariant. Now we look at this and ask the question, okay, suppose I'm looking at a clock which is sending the tick, at every tick of it flashes a light, and I receive it. Okay, that defines what these 2 different delta x's are. First, t, x, y, z is first tick, flash, delta next one is second one. This coordinate differences between these are this delta x, delta t, delta y. Okay, it is moving with some speed v with respect to the map on the road, right? Suppose the clock is not moving. That means v is equal to 0. So when it is flashing, it is not moving. Relative to the map is fixed. So I'm keeping the map fixed. I'm sitting here, and the clock is not moving, it's there. But it's flashing this light, and I'm checking that. It's flashing light every second, so that is delta t of a clock which is not moving. This tells me that this invariant quantity which was there, which I cooked up from somewhere, its physical meaning is that it is the time interval measured by a clock which is ticking and not moving with respect to the map. So on the map, the clock is not moving. The flashing is taking place at some location wherever it is. And that time interval that it defines, that clock reading is what my delta S by C is. So interpretation of what this invariant is obtained by this specific expression. All right. But the same expression now consider another clock. One clock is sitting, which is me, let's say. Another clock is moving. What does it say? It is saying now it's moving at speed v. It has some time. What is the meaning of time? Time is my clock time, not your clock time. What is the interval? Same interval. So therefore, now the interval measured by the moving clock, which is this expression, is delta t times this, which is this. So delta tau moving is equal to delta t, which is same as delta tau at rest. Delta tau is a notion for invariant quantity. This expression is just calling delta tau. Okay. So this expression which is general, which is the time measured by a moving clock, whereas delta t here is delta tau clock at rest. These two are related by this relation. Same expression, I'm just interpreting it. This says that delta tau moving, this number is less than 1, so this is less than that. Which means when this delta clock at rest, my clock says 1 second has passed, that clock is only saying half a second is passed. So it's moving slowly. Which means it's not ticking at the same rate as I am ticking. So the tick rates are changed. Why? Simply because the clocks are moving. Are they physically changing? I have the same watch, you also have the same watch. No machine faults are there. But if I'm comparing the clocks in motion, then I must interpret those ticks and this by this formula. Okay? There's a distinction to be made. Time which is measured and compared versus time which is created locally at any point. These two things are different, they are not same. Because my clock and your clock, as far as you are concerned in moving, I am concerned, nothing has happened to the clocks. Machinery is same. They work exactly the same way. Atomic clocks will also work the same way because atoms behave the same way. But if you are comparing your time with my time, I must make this correction. Inequality? No. That usually one will say that this is the other way around, but this is, that they say, usual expression will be delta t is equal to delta tau divided by square root of it. That delta tau is the tau measured by clock's rest frame. Here the clock is moving. I am at rest. Which one? This one. Tau. No. This is delta S by t. This expression I am calling delta tau. But delta tau as measured by moving clock is the general expression, namely this. See, there are two cases. For the same formula, I am considering two cases. One where the V is 0 and one where V is non-zero. Equation is this equation. This equation is just this from here to here. Yeah, correct. No, so moving is this divide, this number is smaller, no? Right? This quantity is less than 1. When you look at the books, we will do the formula delta tau divided by something. The reason is you are looking at who is defining a time, ticks of a moving clock or a stationary clock. That's the difference. I'm using it deliberately because the next equation I'm going to look at will be easier to understand. This is algebra is trivial. It's the same expression I'm looking at, nothing more. All of you can do it. But that is enough to, you have to pay attention to what exactly are you, what do the symbols mean? And that is enough to give you the answer. Okay, so this is the time dilation. So the clock rates of two are different. How they differ depends on V. And who is V? V is speed of the clock relative to the map which is fixed. I've made my choice. I'm on Earth, I'm doing something. With respect to I'm seeing which clocks are moving because satellites are moving and so on and so forth. Their time and my time should be related, and that's the relation. Okay, that's a very concrete practical problem. Example 2. So is this true? We had this formula, etc. Is this all true or it's all some baloney? You know, somebody invents some formula and say, oh, you do this, blah, blah, blah. Is this true? Answer is yes. Experimental demonstration of the time dilation. Namely, there are elementary particles, muons, which you might have heard of. They have the property that if you're in the lab and you see how they behave, you see they decay typically into electrons and antineutrinos with a mean lifetime of about 2.2 microseconds. So if you have some n of those, after 2.2 there will be half of them. After another 2.2 second, 1/4 and so on, roughly. Okay, its exponential fall is there. So that is roughly they will halve in this half-life. Okay. Now cosmic rays are known to produce muons in the atmosphere, typically between 10 to 15 kilometers above the Earth's surface. And their flux, number of muons falling, reaching the surface, falls by a factor of 2. So whenever I say, okay, that is the muon clock, one tick, number has come half. Let's say somebody is going along with the muon, say, number is half, I set my clock to be tick 1, tick 2, tick 3 and so on. Because it's some physical process I have to choose to define what we mean by ticks of the clock. So if I do that, then the factor of 2 division will tell me that. Now, if time dilation is not true, which means the time done by this procedure and time on Earth is identical, so that the previous expression was all humbug, then there should be almost no muons at sea level. Because if you calculate the time needed for the muon to travel, let's say estimate the maximum speed of light from 10 to 15 kilometers to Earth, number of half-lives you will get, calculate the time divided by 2.2 is about between 10 and 15, which means the flux will be reduced by a factor of about 10 power 4 or 5. Now you ask the question, I have measured it at some height, I measured it on surface, how do the thing match? So if there is no time dilation, I should see almost nothing on the ground, but I see. So therefore, something must be right. Then say, okay, if the formula is right, can I use it to find out what speed they are traveling? Answer is yes, and you find out the answer, and that's the answer. So, but they are and consistent with the dilation formula of speed about 0.98 c. Okay, this first experimental measurement done by Rossi in 1941, a long time back. Yeah, 1 second. Since then, many times, you had a question. In a sense, yes, in the following way. So I am on here in the muon clock, which is, think of the muon decay as a clock. My time is something, its time rate, which is supposed to be 2.2 microseconds in this rest frame. Yes, yes. And from the dilation factor, I know the flux here, flux there, I know how much it is dilated. I measure flux at 2 points. Muons. No. Flux measurement is not done in the rest frame. They decay in the rest frame. The amount of time needed to decay on an average is microsecond in the rest frame. But flux I just calculate in my frame. And my frame I calculate, everything is done in my frame. I calculate flux here, calculate flux there. Decay factor is so much. It must be moving at speed v such that this matches. And that's what it is done. Yeah. You can check the calculation is very easy. Algebra is very simple. Okay. Here's second map now. So that was the first map. Now we'll go to a little more sophisticated and we'll start introducing we are on Earth. So we'll start doing this is map according to general theory of relativity. Now Einstein's crucial insight was that the space-time, which is described previously by delta x, delta t and the metric that we chose, this is actually not God given once and for all, but it determined by distribution of gravitating bodies, gravitating mass. Therefore, a generic mass must be of the form, again it's still quadratic, I'm not changing that, but that previous Gij, which were specific numbers, the one that I wrote earlier, 111, it is now more general, which may depend upon where I am measuring this. So T, X, Y, Z. So it is not constant everywhere, unlike the previous case, where it was always -1, 1, 1, 1, or 1, -1, -1, diagonal. This need not be diagonal, this need not be fixed to this. These metric coefficients are supposed to be determined by Einstein's field equations. That's a separate dynamics of general relativity. We are not going to talk about that. We are going to look at the kinematics of this because all we need for our purpose application is that. Okay? Alright, so this is to be determined by that. That's Einstein's theory. So that GR you will study when you go to appropriate graduate school, etc. But this is what the nutshell is. This number has to change, this set of numbers have to change, and they change some fashion, but of course I must have some rule to decide how to choose it in a given situation. Because today I am looking at near the sun, tomorrow I am looking at near the black hole or whatever is the other star. How do I know what GIJ is to be chosen in a given physical situation? So there must be some equation. That equation is Einstein's equation. Okay? Complicated and so on, never mind. So here's an example of a GR map. So near a spherical body, like a mass m, so like a sun, the map is specified as, again, delta S square, like we previously wrote. But now it is in terms of, the coefficient is not 1 anymore, but it's 1 minus 2 gm by c square r. Okay, r is the distance from that. G is the Newton's constant, m is the mass of the body which is sitting there, and c is the speed of light. This is multiplied, the second term is, this coefficient is not 1, unlike the previous case. And then this is r square, this because I have chosen the, instead of xyz coordinates, I have chosen r theta phi coordinates. So that's just a simple going from using spherical, yeah. Phi is the, so, So earlier in the two-dimensional case I showed you, right? This was my coordinate x, y, or I chose this r and theta. Right? So this point, instead of labeling by x, y, I can label it also by r and theta. And you know the relation between them. If you are on a sphere, you say that I can either look at it as, let's say, this is x, this is y, this is z. And any point here I can denote by 3 numbers x, y, z. Or I can say that I draw a line from here, call this r. I measure the angle between these two, called theta. And I drop a perpendicular on this plane and measure this angle, call this phi. So instead of, this point will be labeled as r theta phi. Okay, that's a different way of labeling the same thing, but that's what it is. It's exactly like this, except that little more complicated. Yeah. Okay. Now, so this is now new map. We are going to ask the same questions. What does the t mean? And what does delta s mean? Delta s is invariant. That we agreed. This left hand side is invariant. Where does this come from? You solve Einstein's equation. In particular case, you will get this form, etc., etc. So that part we are going to assume. We are not going to do the calculation because we don't need to. So if this is the case, now this is what happens. Now t is the time assigned by a clock at rest. So first of all, I put the clock doesn't move. Okay. So my delta t, which is coming by, delta r, delta theta, they are all 0. Because the clock is it has same r theta phi coordinates now and later. So delta t therefore is the clock, time measured by a clock at rest. But it is now at some location r, because it depends where you are. Okay. So if I take r going to infinity, then this term will drop and I will just get delta s is equal to just c delta t square. Which means just as the previous time, delta s by c was the time measured by a clock at rest relative to map. Here also is the clock, time measured by a clock at rest, but kept at infinity. Because now there is r dependence. Previously that did not exist. Understand? So a clock here and clock there, they will click differently. But clock at infinity has this value because this term will drop out. This term will drop out for r is very large. So then delta t interpretation is the time measured by a clock at rest related to the map and very far away from this gravitating body. Ideally infinite mathematically, but physically it's sufficiently far away. Okay, is that clear? Okay, so now take another clock. Again at rest, let's say I can make it moving also, that will make life more complicated in formula. I take another clock, but which is not far away, but is nearby. Say Mount Everest or something, or some building which is there. Okay. Now what will happen? These terms are still 0. These terms are still gone because the clocks are at rest. These terms are not there. But now this coefficient is there. So this is going to be 1 minus 2gm by c square r. R is the location of the new clock. So two clocks, one clock is far away, other clock is at a distance r, coordinate r. The two clock rates are, if the clock, the time measured by the clock at location r is delta tau r. Delta tau infinity, this coefficient is just the tau time measured by clock at infinity. They are related by this factor. Same formula. Exactly same thing that we did before. And this number is less than that. Therefore, delta tau infinity is larger than delta tau. Therefore, clocks closer to gravitating body run at a slower rate. Okay. This is something, this is larger. So when the far away clock says 1 second is there, this guy only says half a second has passed. So this clock is slower. Okay. So this formula alone is enough to explain how to relate the two clocks. Okay, and depends upon where the clock is located. Okay, so that's because there is a gravitational field. Previous case did not exist, but now gravitational field do that. Once again, I can ask the same question: is this all baloney or is something real there? How do I know experimentally true? That's the one. Experimental demonstration. This so-called Pound-Repka experiment, which was done in 1959, long time ago. Many things are done long ago. Here you say that light or photons falling from a height, so some height is there. As they fall, because of gravitational potential is there, they gain some energy, which means the energy is going to be different. And for a light, quantum mechanics tells us that the frequency is nu, and energy is h times nu. So if it has gained more energy, its frequency has changed. All right. But now if the frequency has changed, so I have some atoms which are nuclei which are emitting light from there. I have same nuclei at the bottom here. The frequency of light emitted is fixed by the energy levels of that. Same energy levels if there, then the light will be absorbed, otherwise it won't. But the light has gained energy, so it has frequency change. Now it cannot be absorbed. So if I send light from there, in this case gamma rays, if I send them from the top, they won't be absorbed here. So I ask the question, I'm sending it here, how many things are absorbed here? Nothing will be, almost nothing will be absorbed, or very little. Because the frequency has changed, energy has changed. That's because of gravitational effect. That's what is expected. All right, but then how do I make sure that? I can keep this source moving. I can move this source a little bit up and down at some known frequency, known speed. Then as it moves, because of Doppler shift, the frequency will change again. Sometimes it will increase, sometimes it will decrease. So now I have variation of the frequency as a known control of the motion of this source. So I know how much is the detection rate I should get here. I should see the absorption rate up and down as with this frequency. Ask the question, when is it maximum? It will be maximum when the energy levels precisely match. And that is which will tell me how much is the shift which has come from there to there. And that shift will tell me whether the clock is right or not. The gravitational time dilation formula is correct or not. Okay? Because if it is not correct, then I should just see the Doppler shift thing only. So it will only when it is stationary, it will show the absorption. Otherwise it should not. Because the energy is same. In fact, Doppler shift, if it is moving, nothing should be absorbed. Suppose there is no time dilation. Then the frequency there is same as frequency here. Because the energy levels are same. So the gamma rays emitted from there should all get absorbed here. All meaning 99%. If I keep them moving, the frequency is going to change of the light, which is gamma rays. If it is more, it's not going to be absorbed. If it is less, it's not going to be absorbed. Which means I should show no absorption as long as it's moving. I can track it and say, change the speed to some unit, then for 2 times that, 3 times that. I see nothing happens. It just doesn't get absorbed. However, if there is a time dilation effect, this thing will shift. It will be absorbed at different speeds. So as a function of speeds that I choose, I will get different absorption rate. Earth's gravity. Earth's gravitational field is there. This is done on a tower. This is so let's say it uses this particular gamma ray whose energy is known, 14 keV. These are details of the experiment from iron 57 isotope. Height is 22.5 meters. So there's a tower at which this source is kept, and they're finding out the gamma rays coming down. And these are technical details as to how you will actually measure, how many errors are there, etc. So there's a lot of details are there. I'm just giving the schematics of this. Logic is that if there is no time dilation, then because the frequency should be same, I should get full absorption. If there is no movement. But if there is a movement, frequency is going to change because of Doppler effect. If it's going to change, I should see no absorption because no frequency is not matching. Unless the atom, the light incident on the atom has energy corresponding to the energy levels, it will get absorbed, otherwise it won't. Right? So if I change the frequency by Doppler shift, I'm not going to get absorption. However, suppose there is a time shift, so this energy levels effectively have changed a little bit. Now it will happen for some speeds. Other speed it will go to off. So I will find out the speed at which I get the maximum one. So I know how much shift has taken place, because speed will tell me how much frequency has changed. That frequency change is attributed to gravitational field. And from that I infer how much is whether the formula works or not. Think about it a bit, you will be able to figure it out. It's yeah. We'll come. I will answer that little bit later, because in satellite case we'll need both. Okay, I'll come to that in a minute. Here, this is just an example that given the metric, given the map, which I need the map, I need the metric, the coordinates. I'm explaining just given this information, how do I find out that the laws of physics will tell me that 2 clocks do not tick at the same rate? Special relativity will tell you it's because of the speed. General relativity tells me it's because of gravity. If you have both, the clock is moving arbitrarily, wildly, you are getting both effects combined, your formulas will be more complicated. They are available, they are easy to calculate. This is the simplest way to see how it happens. Okay? Alright? So Mossbar effect is something which says that because when the photon is emitted, is going to also change the momentum, that will add extra drift in the speed, blah, 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 etc. So let's skip all that. But there is something called this. This was also essential before you could distinguish this, because this requires accuracy of 1 part in 10 power 15 or so, which can only come with the mass power effect. Okay, summarizing. Compared to a clock on Earth, a clock in orbit runs faster due to gravitational time dilation, because farther the clock from the body, the rate is faster, right? But it's slower because the special relativity says that it's moving. So the time dilation will say it is slower because of the movement of the clock. For a circular orbit of radius about 9,545 kilometers, the two effects exactly cancel. So the clocks will be synchronized. Okay? This calculation is easy. I mean, you just use the formula, put in the numbers of mass of Earth, you will get the answer. They're very easy. Remember only that when you calculate the two clocks, one clock is in the satellite, second clock is on the surface of Earth, which is not at origin. So radius of Earth also. You have to compare two clocks at two different radii, take the ratios, clock at infinity will disappear and you will get the answer. And that numbers also expand 1 minus x, square root is 1 plus minus half x, etc. You will get the answer. Answer is straightforward. Algebra is very simple. So this was, so clock rates do affect, both of them are there, but the sources, the reason for them, they're different. And you can distinguish them by looking at how it varies with speed or how it varies with the location. Okay, so what finally is the appropriate map for the GPS? So now we assemble thing, we know these things are there, satellites are going, and we know satellite clock speed is going to change because of these two effects. So having gotten all of this, now to say, all right, I want to now design my system, put the satellite somewhere, I must pay attention to all of this, and then I will get the answer. So what is the final appropriate map for GPS, which means what is the coordinate system, what is the metric? That's all I need to know by my map. Here it is. This map for GPS, Earth-centered inertial frame. So now you imagine Earth is not exactly spherical, it's slightly ellipsoidal, and it's rotating. I have not talked about rotation. Okay, that's one more feature is there. Momentarily ignore it. If I just imagine the Earth is there and just ignore it is there, and just concentrate all the mass at the center. So my coordinate system is centered at the center of Earth. That's my R. And my axes are not rotating with the Earth. They're fixed. So that's the Earth-centered inertial coordinate system. In that, using that, I'm assigning my T, X, Y, Z coordinates or T, R, theta, phi coordinates. Like that sphere, the origin is at the center of Earth. Okay. Then this is similar to what we had before. There are minor changes. This thing is not GM by R, but it's some little bit different. These parts are the same. And this is also a little bit different. Okay. And the V of this is given by this particular first term here is what we read earlier, which is the spherical Earth completely. But if it is not completely spherical, it's slightly bulged, then there is a little distortion, and that comes by this quadrupole moment, and then the algebra formula will come. You will learn that when you go into classes and so on. The fact is, just as those formula we assume, we take that this is something which is determined separately before we do GPS and all that. I simply have the Earth which is of this shape, so I know how to find out a metric for that. So this is what it is. These numbers are there. I'm just making them to show that how they are. That's all. I mean, you don't have to remember any of this. And the radius of Earth is the equatorial radius, which is so many meters. You can make decimal places and so on. And phi naught by C is subtracted here. Unlike the previous case, this was not there. That's because when you talk about 1 second, that second is defined in some particular laboratory on Earth. That laboratory has, this is Earth, it has a shape, and the surface of this big equipotential will be roughly of that shape. So the potential, gravitational potential will be same along the surface, roughly. Okay? So it is not going to be same across all the locations on Earth. So it's going to vary from place to place. You say wherever the lab is, I know it's r theta phi coordinates. I put that correction, and that is my phi 0. This is at the location where the second is defined. So you make to incorporate that correction, and this is what you get. Okay. Now from this you can calculate all your time dilation, etc. Same thing, what we did before, exactly same. Okay, because all the machinery is there. The J2 signifies that Earth is not exactly spherical. The extra term phi 0 is added to incorporate the fact that our standard unit of time, the SI second, is defined by atomic clocks at US Naval Laboratory. This number might have changed now, because I think now the standards are shifted elsewhere. So what this detail I don't know. I have not verified it. What is the current standard? This thing was in France there is this International Bureau of Standards. So there are multiple places. That's a separate thing, how the clocks are synchronized. That's a very, very sophisticated, quite interesting stuff. That will be a separate talk in itself. So I'm not going to talk about that. I did go through that to find out. It's quite fascinating. And you will see how sophisticated it is. Okay, so this is for the moment, this 5 knot is there because this was the actual GPS which was in practice then. Is still available, so that's what they use. So this is specific to that particular GPS. If I have a different navigation system, there are many, Russian is there, European is there, Indian is there, Chinese is there and so on. They will not be using this formula. They will have their own formula. Okay. So, because they will define, so the 5 knot will change from which second you are, wherever you are defining, not naval observatory, maybe somewhere else. But you have to synchronize all of this. They must be related in a specific fashion. Once that is done, then synchronization is over. Okay, so this for that. Now clock rates are precisely determined by once the satellite orbits are known. Because I need to know the speed and height. So I must know the orbits of the satellites very precisely. But satellites being satellites, and this happens, space weather is there, all kinds of, there are some variations are there, the speed will adjust a little bit, friction is there. So you have to keep correcting and tracking it. So know not only enough to say that my mathematics says satellite should be here. It's here but slightly away. So I must actually measure it by ranging and say it is here and is moving at and I must update this information every 2 hours or something. So that is called tracking of the satellites on ground-based systems to see what it is, to know where the orbit is. And that information is transmitted by the satellite signal to your device. So all that information has to be used. Okay. Now, it so happens that at the time of launch, the rates on the onboard clocks are deliberately slowed down so that once they are in orbit, the rates match to those on the ground. So when you set the clocks, you adjust frequency such that once they are in the appropriate place, now they are ticking at the same rate as you are ticking here. Okay. What happened? So here are some actual details of the actual GPS system. Okay. So far it was schematic to some extent, even now it's a little schematic. I can't go into every single detail, it's just too hard. So this is Navstar GPS, information available in Wikipedia, you can see it. So this stands for Navigation, Satellite, Timing and Ranging Global Positioning System, blah, blah, blah. It is operated by US Department of Defense. This is the one which is, in a sense, the oldest system which has been there. It has 24 satellites in 6 planes to the center of Earth, each making an angle of 55 degrees with the equator. So this is Earth, this is the equator. I take one plane like this, 55 degrees here, another plane 55 degrees, third plane 55 degrees. And in each of the plane there are 4 satellites, roughly equidistant. That's how the configuration of 24 satellites is. Why do I put this configuration? One is stability of the orbit. Secondly, from any location on Earth, I should have at least 4 visible all the time. So I cannot say that it's visible only in northern hemisphere, not in southern hemisphere. So I must make sure that the orbits are so chosen that this is true. And that is true. In fact, in Wikipedia article, you will see a simulation or animation of the actual GPS satellites. I was first thinking of getting it, but I could not adjust it to show it on this. So I said, okay, I will just tell you. You can see it on that. So roughly 90 degrees apart, that's what it is. The orbits are nearly circular. How far are they? They are 26,600 kilometers above the Earth. Okay? And the orbital period is almost 12 hours. Okay? So this is the period of the actual satellites though. And at that level, with that speed, what are the time differences? These are numbers. Special relativity, because of Doppler speed, it will reduce because slowed down by 7.2 microseconds per day. So per second it will be like 10 power minus 10. So roughly 10 decimal place, numbers will change. And because of relativity, general relativity, gravitational field, it is plus 45.8 microseconds per day. If you don't make these corrections, then your synchronization will be off, and within a couple of days, your ranging distance measurements will all be off. So suppose Einstein did not come, didn't tell us relativity, but somehow we managed to get these satellites by other method, then they'll say, oh, we'll have to make this incorporate correction, otherwise it will not work. We're lucky that Einstein gave the theory, etc., and we know it. So we can calculate before launching it. Otherwise, funding will be a problem. I mean, how do you know it will work? So this is something which is there. So at least 5 satellites are visible at any time from anywhere. That's the reason for that particular configuration. The other systems which are there, like Russian, European, and so on, these three and Chinese, they all are still global, the coverage is global. But their configurations are different. They don't have 6 planes, only 3 planes, and orbits are different and so on. Indian one, which is started now, we are not completely done yet. That has, I think, 7 satellites are supposed to be, of which 4 will be there. But our range is limited. Our country and 1500 kilometers away from that. Because we don't need to be global. Japan is also a similar regional tracking system. Again, with fewer satellites, you don't need so many satellites. But they are different systems. The oldest one is this. Russians one also started almost immediately. But that did not, it became quiet for several times. Now they have their own. We are doing it because in case of wars or something, you don't get these precise signals. Apparently it happened for Kargil war. US refused to give us the precise code. So we could not get the locations appropriately. So we said, all right, we must have our own ranging so that we are not denied this accuracy. Okay. So each satellite broadcast, I'm almost on the 5 minutes or something I need, 5-10 minutes. Each satellite broadcasts a radio signal at 2 carrier frequencies. This is the amount of data that it gives, consistent of so many blah, blah. So it says which satellite, which identification code, what is this orbit, where is it good or bad, is it healthy or not healthy, or there any erection there, and whatever corrections have to be applied, this information is given there. Orbit data is updated every 2 hours. I told you that you have to watch the satellite and say where it is. Tell the satellite you are here, satellite makes corrections in the program, send the information and so on. So what are the estimated errors from all the places? There are all kinds of errors involved. One is inference of time delays, how you calculate that, because the orbits are different, radii are different, etc. So there could be little deviation in that. Ionospheric delays, light has to come from there, it has ionosphere in between. That is electromagnetic charges are, electromagnetic waves are going to be affected by that. That will contribute 5 meters of inaccuracy, this is 3 meters. Orbital data all said and done will still have something, that will be 2.5 meters. Satellite clock errors, they are not precise. Every system has errors in it. That's a fundamental rule we should remember. Mathematics will tell you exact expression, they are never true. They are always, actual thing will always have to be some errors. They are very small, but they have to be paid attention to if you go to higher and higher precision. This doesn't mean you don't do exact calculation. You need exact calculation for a different purpose to estimate how much is the error. Okay, so both are necessary. Tropospheric effect, multi-path distal light may come, get bounced somewhere before coming. That is 1 meter or so. All of this added contributes to about 15 meters. Okay, that's totally add it up, it will be about that. Okay, so that is the GPS part which is there. Once the system is there, you incorporate that, you know anywhere on earth where you are, and that is location you have. And therefore, once you know where you are, your location, I know the distance between you two. So clocks at one location, clocks at second location, third location, they all know how much distance is there. So if I send a signal, how much time delay will be there, that is known. So now we come to the time distribution. So the second part of the question that I rose. Basic steps are the following. National laboratories in various countries maintain a bank of several atomic clocks. I put in double quotes, it's not one kind, there are multiple types. There is cesium clock, there is rubidium clock, there is fountain clocks, and some optical clocks. All kinds of things are there. Half of them I don't know, most of them I don't know. But they are there, and each one has its own specialty and how it is designed, what accuracy it has, how stable it is, blah, blah, blah. But typically they will have stability of 1 part in 10 power 16. So 10 power 16 seconds, each year has about 10 power 7 seconds. So billion years, it will lose 1 second. That is the stability that it has. The rate will be so fixed up to that. The average of all these clocks is then taken, defines what is called a local time. When a particular laboratory says, this is, as far as I am concerned, this is the rate, this is the time I do. What time, where do I start counting? That I will synchronize somewhere else. A suitably weighted average of about 450 atomic clocks. There are some 80 laboratories all over the world. They are taken together and defined as an international atomic time. There's a committee which meets every often and decides all this. By incorporating corrections of leap second, coordinated and universal time is given. And that is the time which is typically transmitted to various places, be your mobile towers, be your internet service provider, which then transmits to your mobile and say, this is what the time is. So schematically, this may be viewed as counting the number of seconds that have elapsed since the chosen starting point. So choose some starting point, and this tick will tell me 10,000 seconds have gone, 15,000 seconds have gone. That number it will tell. That's what the signal means. Signal is more, but as far as schematically, this is what it does. Okay, UTC time says This is broadcast by various means, radio signals from satellites, wired signal from telephone networks, microwave mobile towers. You can query ask the question, no, give me time of the day. The computer will give it. How does it give? It takes a local clock. How does the local clock know? Gets it from service provider. How does that know? It gets it from UTC. So all these places it comes and finally you get an answer here. Okay? So clearly there is a delay involved in all these places. But the signal is coming from, let's say, France. It is going all over the place. Distances are different. Speed of light is finite. So there are delays involved. But the delays are known because I know the locations. And the locations are known because I have GPS. Once the delays are known, I say, okay, I have received signal from there. I am the one which is giving it to your mobile. This is time, I subtract that time from the signal because it tells me this is such and such date. 10 o'clock, 30 seconds, whatever. I subtract that time delay and send it to you. Then you take that time, this is time, I reset my local clock, I am done. So, to do all of that, that is what the synchronization part is. So, however, this is precisely known thanks to the positioning system such as GPS. The delay subtracted is retransmitted, a local device receiving signal resets its internal clock and synchronization is achieved. Thus, where am I also answers what time is it. So, that was the starting point. You need that question, that if you know the answer to that, you also know what time is it. And both rely on relativity and quantum mechanics. Without that, quantum mechanics I didn't talk about, but atomic clocks maintain their stability and precision because of quantum mechanics. This is the year of International Year of Quantum Mechanics. 100 years are completed from discovery of quantum mechanics. So I should say that. So both of these theories which are there, which are considered as esoteric theories and very philosophically disturbing, whatever, blah, blah, blah. Ignore all of that. If you don't have it, you don't have your time here. So, thank you. Any questions are there, please? Yeah. Yeah. Yes. Yeah. Yes, yes, yes. So you cumulatively add that. So speed of light will not be exactly same as speed. That's correct. So that will precisely. So because it's passing through medium, so there will be refractive index and speed will be little less. I agree. So you calculate all that by knowing the model of the atmosphere and measuring the atmosphere itself. So you will know that. All that is converted into how much error it will contribute. That is the final answer is given in terms of how much error it will do because of this ionospheric delay will be precisely because the speed changes. Yes, yeah, that's where the charges are. That's where the speed will change. The ephemeris error is because of the motion of the tracking itself will have error. Tracking of the satellites, where the location is. I need that to know the speed as well as the R. Clock themselves are errors. I mean, there are some limitations how precise the clock can be. There are quantum mechanical limitations on that. Multi-part distortion. Light may not come directly to this. It may bounce somewhere and so on. That means it will add a little bit. Tiny amount. But we are talking about 1 part in 10 power 10. Some errors will. So it will equivalent distance will be multiplied by standard speed of light will be 1 meter distortion. So that's why all these errors are, they're identified sources and they are validated, calibrated and so on. So this is the estimate is. And you can also reduce the error by not looking at 4 satellites but 5 satellites and 6 satellites. They can average, the errors will be reduced. You can also use additional information from local thing. So to reduce the minimizer, they are called enhanced GPS and so on. So there are methods of doing that. But those are more engineering related things which are relevant practically. But my purpose here was to show how the really basic things, they come relativity and quantum mechanics, how they enter, and they can be introduced without having to know whole machinery. It's enough to just know what is the problem, how you break it up, and how do you get from there. So that was the purpose of this. Yeah, anything else? Any other question? Yeah. Yes. Yes. Numerical errors. Last one, 1 meter. Truncation errors will be there. Yes, absolutely. Yeah. Yeah. Yes, so you will know, so before you start using the system, you calculate all this in estimate. I didn't talk about the effect of the rotation. That's called Sagnac effect because Earth is rotating. So light going around one way and light going around one way, there is a time difference. That's called Sagnac effect. I didn't talk about it. That correction is applied in your mobile device, not by the guys who do it. I just didn't mention because there are already so many things are there. So that is there. So if you go through that, I mean, you'll see variety of things. But again, although taken together, it looks very complicated. In a sense, it is. It has many steps. It's complicated in a sense there are multiple steps. But each of the steps, if you understand what is involved, is not that difficult. It's relatively simple. But you have to break it up properly and see how do I think about it. And then algebra is very simple. What I did was anybody can do it. Very, very simple algebra. Except when you say, why did you get that particular solution? Well, then you have to do the calculation. But modulo that. But you never do that. I will start from Newton's laws and derive everything. Somewhere you say, I start from here, do the calculation. I will postpone this to later part and so on. Yeah. Any other question? So I think I started a bit late, so it's okay. I'm in time. Okay, so I can take off my